Hey everyone, welcome to my first video. I recently became interested in noise and how it can be used in programming. In this video I'll explore how noise works and how it can be applied to create art and simulations. Randomness is essential. It makes video games entertaining to play and it's used in simulation programs, such as particle systems. However, this randomness is easily discernible from the randomness we see in nature. It's machine-like. For example, if you wish to procedurally generate terrain similar to land on Earth, it would be difficult to do so with classic random number generators. Ken Perlin noticed this shortcoming of random number generators and developed Perlin noise in 1983. Perlin noise can be thought of as smooth randomness. It's organic and more closely resembles the randomness we see in nature. One way to use Perlin noise is with the processing library. The noise function accepts up to 3 arguments describing the position in the noise space. If you need one-dimensional noise, you pass in an x value to the function and it returns the noise value at that point. If you then increment this x value over time, the noise function samples noise values at different points in the noise space, and you get this sort of smooth randomness. The greater the increment value, the greater the distance between different noise points, and the stronger the noise. Now, let's say you wanted to produce a 2D plane of noise. The noise function can accept 2 arguments, an x and a y value, which you can use to get 2-dimensional noise values and color pixels on a screen, according to the noise value at the xy position. 2D noise looks like this. To create this image, I loop over all the pixels on the window and keep track of their x and y positions. In processing, the pixels array keeps track of all the colors of the pixels on the screen. I use this formula to convert between the x and y location and the index I of a pixel. I then get the noise value at this x and y position, scaled according to the frequency I defined, and map the noise value between 0 and 255 to be used as a grayscale color. If I change the frequency, the noise plane scales up and down, becoming more or less detailed as a result. What if I wanted this noise plane to change over time? I could make use of the third noise dimension. In this image, I'm getting noise values from a 2D noise plane. However, if I move this plane over time in 3D space, I would get a changing 2D noise image. I can add a z variable to my code, add it as an argument to the noise function, and increment it in the draw loop. You can think of this z variable as time. The faster it changes, the faster the 2D noise plane moves through space, and the quicker it appears to change. This noise is great. But to get more intricate and varied detail, we can use a technique called layering, also known as fractal noise. By adding together different layers of noise at different frequencies, each one contributing less and less to the final sum, we can get more interesting results. Here's the general code for layered noise. The number of octaves is the number of layers. Frequency starts at some base value and increases according to the roughness variable. Similarly, the amplitude starts off at some base value and decreases according to the persistence variable between 0 and 1. Each noise value is added together and the final result is returned by this function. This particular noise has a roughness value of 2 and a persistence value of 0.5. Now, I need a way to color this noise. I can start off with a 2-way gradient, but this quickly becomes repetitive. To make things more interesting, I created a gradient class that has 2 attributes, an array of colors and an array of floats. Upon creating a gradient object, I can pass in a set of colors that I want my gradient to contain, and also an array of floats representing the bounds of this gradient. For example, let's say I wanted a 3-way gradient between these colors. If I set the bounds to be 0, 0.5, and 1, the middle of the gradient will contain the second color, and the beginning and end will contain the first and last colors, respectively. By changing these bounds, I can skew the gradient towards a specific direction. To test my new class, I wanted to try and recreate water caustics, which are patterns produced at the surface of water due to the reflection and refraction of light. To do this, I decided to go with another noise algorithm called Open Simplex Noise, implemented in Java by k.jpg. I combined fractal noise with this 5-color gradient to achieve this result. Finally, I want to mention a technique that's used to distort noise. This is called domain warping. The way domain warping is accomplished is by offsetting noise by using more noise. For now, what we're doing is sampling noise values at specific points in space by using x and y coordinates. The idea of domain warping is to offset these x and y coordinates using more noise to get a distorted effect. So if p is our point in space, and n is our noise function, we can define our offset, O of p, to equal n of p. Then, when calculating our final warp noise value, W of p, we take n of p plus our offset. So domain warping works with function composition. This is what the code looks like. I separated the x and y offsets to make it more clear, and I multiply the offsets by some scalar to increase the warp effect. I also offset the offset noise by some amount to increase the noise variation. If you would like to play around with this code, feel free to visit the GitHub repository. Link is in the description. There are an infinite amount of things you can do with these tools. Here are some of the things I came up with by messing with the noise parameters. Anyway, that's the end of the video. I hope you enjoyed it. See you in the next one.